Hi, my name is Megan, and today I'm going to show you the differences between a sequential and parallel FIR and FFT on the UCLA Linux server. So UCLA Linux Server 9 has 32 cores, and if you run it with 16 threads and 4,096 elements, the parallel FFT take a slightly longer time than the sequential FFT. It's still all in nanoseconds. So the sequential FFT took about 700,000 nanoseconds, and the parallel took about 900,000. If you run it again, now they've taken about the same amount of nanoseconds. So with 16 threads, the timing's about the same. So if we change the number of elements to 65,536, and we run it again, now we can finally see the speed up for our parallel FFT. So now the sequential FFT is taking about 12 million nanoseconds to run, while the parallel FFT is only taking about 4 million. If you run it again, we get about the same results. So this is a 3 times speed up at least for the parallel compared to the sequential. So now we're going to do the same thing with the FIR function. So now with 16 threads and 4,096 elements, the parallel FIR function is taking 23 million nanoseconds to run, while the sequential FIR function is taking almost 200 million nanoseconds to run. This is a big difference. So this is almost a 10 times speed up. If we do it again, it's about the same results. And once again, the same. So now, if we change the amount of elements to 65,536, we can see a real difference now. So now it's actually taking more than a second to build, unlike before, which was pretty instantaneous. Okay, so finally we got our results. The sequential FIR took 50 seconds to run, while the parallel only took 3. So this is a big difference right here. So I'm not going to run it again for time's sake.
This is Jack, and I will be demoing our code running on the LCCDK and CCS9. So we use RTOS for timing of our functions. And to get RTOS set up with CCS9, you have to follow a series of steps to create what's called a configuration file. And the configuration files contain a bunch of stuff to initialize RTOS environment variables and so on. So this is an example of a configuration file from following Rahul's instructions for RTOS. And this is the IPC configuration file we were trying to use when working with IPC, but it didn't work out. So yeah, on the left, all the files with the cross through it means it's not active. And since we're not doing IPC, we made it inactive. So now I will be running our code for the FIR for data sizes 8 to 2048. So on the right is user-defined is the target configuration. The target configuration file is a result from the .cfg file, and that's how you start everything. So let's do that. Okay, so on the right side here in this window are the targets. So the targets we want to connect are the cores on LCDK. One is the DSP, which is this one right here. It's connect target. And the other one is the ARM core. So let's also connect that one. And now to run it in our main function. So I've temporarily commented out the FFT code, and we're gonna do the FIR first. So we're gonna start. So here down here is how we run the function that tests the FIR. So in RTOS programming, it's based on tasks, and tasks are kind of like a function. So this is the code to create a task. You do it in the main function, and then it runs it. So we're running FIR test, hence all this code here. Now let's get started. So these are all the constants and data arrays for the FIR. That's the FIR.